I hope I am audible to all of you. Hello. I hope I am audible to all of you. Okay, then let us start. So, what we'll do is today, uh, basically, the last class we discussed certain points about SFP and BMP. And, so, let us start with some new videos and all. So, I'll show you that one and then we'll discuss it eventually. That your basics be clear. Can you see my screen? Can you all see my screen? Can you all see my screen?
Sir,
Okay.
Are powerful graphical methods that shear force and bending moment diagrams are powerful graphical methods that every mechanical and civil engineer should know how to use to analyze a beam under loading. In this video, I'll explain exactly how to master these diagrams, and we will see how they can be used to understand how a beam is loaded. I want to start by explaining what shear forces and bending moments actually are. When a beam is loaded, internal forces develop within it to maintain equilibrium. These internal forces have two components. We have shear forces, oriented in the vertical direction, and we also have normal forces, which are oriented along the axis of the beam. If the beam is sagging, the top of the beam will get shorter, and so the normal forces in the top of the beam will be compressive. The bottom of the beam will get longer, and so the normal forces in the bottom of the beam will be tensile. Each of the tensile normal forces has a corresponding compressive force, which is equal in magnitude but opposite in direction. As such, these forces don't produce a net normal force, but they do produce a moment. This means we can conveniently represent the internal forces acting on the beam cross-section using just two resultants. One, shear force, which is a resultant of the vertical internal forces, and one bending moment, which is a resultant of the normal internal forces. This is a very common way of representing the internal forces within a beam. Drawing the shear force and bending moment diagrams is just figuring out what these internal forces are at each location along the beam. These resultant shear forces and bending moments will depend on the loads acting on the beam and the way in which the beam is supported. Beams can be loaded in a number of ways, the most common being concentrated forces, distributed forces, and concentrated moments. Beams can also be supported in a number of different ways. They can have pin supports, roller supports, or be fully fixed, which each restrain the beam in different ways. Pin supports prevent vertical and horizontal displacements, but allow rotation. Roller supports prevent vertical displacements, but allow horizontal displacement and rotation. Fixed supports prevent all displacements and rotation. If a certain degree of freedom is restrained at a support, we will have a corresponding reaction force or reaction moment at that location. For example, rotations are permitted for a pin support, so there is no reaction moment, but displacements in the vertical and horizontal directions are prevented, so we will have horizontal and vertical reaction forces. So how do you determine the shear forces and bending moments within a beam? There are three main steps we need to follow. First, we draw a free body diagram of the beam. This shows all of the applied and reaction loads acting on the beam. The next step is to calculate the magnitude of the reaction forces and reaction moments at all of the beam supports. We do this using the concept of equilibrium. To maintain equilibrium, all of the forces in the vertical and horizontal directions should cancel each other out. Similarly, all of the moments acting at every point along the beam should cancel each other out. This gives us a set of simple equations we can solve to calculate the reaction forces and moments. If we can calculate all of the reaction loads using the three equilibrium equations, the beam is said to be statically determinate. For some beam configurations, like this one shown here, we won't be able to calculate all of the reaction loads because we have too many unknowns and not enough equilibrium equations. In this case, the beam is said to be statically indeterminate. This beam has 4 reaction forces, but we only have 3 equilibrium equations. To solve this beam, we would need to use slightly more complicated methods and consider boundary conditions. In this video, I will only cover statically determinate cases, where we can use the equilibrium equations to calculate all of the reaction loads. Once we have calculated all of the reaction loads, the third and final step is to figure out the internal shear forces and bending moments at every location along the beam. To do this, we will use the concept of equilibrium again. If we cut our beam at any location, the internal forces and moments need to cancel out the external forces and moments so that equilibrium is maintained. This allows us to easily calculate the shear force and bending moment at each location along the beam. All we need to do is start from one side of the beam and move the location of the cut along the beam, calculating the shear forces and bending moments as we go. Now is a good time to define the sign convention we will be using. Applied forces will be positive if they are acting in the downwards direction. For shear forces and bending moments, the positive sign convention will be as shown here. If the beam is on the left side of our cut, shear forces pointing downwards will be positive. If the beam is on the right side of our cut, shear forces pointing upwards will be positive. Positive bending moments will be those that put the lower section of the beam into tension. Another way to think about it is that bending moments which cause sagging of the beam are positive, and those that cause hogging of the beam are negative. Let's take a look at an example of a beam with pinned and roller supports, loaded by 2 concentrated forces. First, we draw the free body diagram. We can then use the equilibrium equations to determine the unknown reaction forces at point A and point B. The sum of the forces in the vertical direction is equal to 0, So RA plus RB is equal to 15 plus 6. Because HA is the only horizontal force, it must be equal to 0. We also know that the sum of the moments about any point along our beam must be 0. Let's consider the moments about point B. That gives us this equation, which we can solve to determine that RA is equal to 12. By substituting RA into the previous equation, we can deduce that RB is equal to 9. Now that all of the external loads acting on the beam are defined, we can draw the shear force and bending moment diagrams. We will start from the left-hand side of the beam. Let's draw the free body diagram for a location immediately to the right of the 12 kilonewton reaction force. To maintain equilibrium, the shear force must be equal to the reaction force. We can draw this on our shear force diagram. The shear force will be constant until we reach the next applied force. The bending moment must be equal to the 12 kilonewton reaction force multiplied by the distance x to the reaction force. This gives us the equation for a straight line, which we can draw on our bending moment diagram. We then repeat the process by moving the location of our cut further to the right. This time we place the cut immediately after the 15 kilonewton force, and we draw the free body diagram again to determine the shear force and the bending moment. We repeat this process until we have covered the full length of the beam. We end up with the complete shear force and bending moment diagrams for the beam. That example was a fairly simple one. For cases with more complex loading, drawing the shear force and bending moment diagrams can be more difficult. There are relationships between the applied loads, shear forces, and bending moments, which will help us better understand what our diagram should look like. Let's consider a beam loaded by an arbitrary distributed force. We can zoom in to look at an infinitesimally small segment of the beam with a width equal to dx and draw the free body diagram. Over such a short section of the beam, the distributed force can be assumed to be uniform, and we can replace it with an equivalent concentrated force. By applying the equilibrium equations to this free body diagram, it is possible to demonstrate that the following relationships exist between the applied distributed force, the shear force graph, and the bending moment graph. The quantity dV over dx is the slope of the shear force curve, and at a given point along the beam, it is equal to minus the distributed force. Similarly, dm over dx is the slope of the bending moment curve, and at a given point, it is equal to the shear force. If we integrate the first equation, we can show that the change in shear force between 2 points is equal to the area under the loading diagram between those 2 points. And if we integrate the second equation, we can show that the change in bending moment between 2 points is equal to the area under the shear force curve. This is really useful information we can use to help construct or sense check our shear force and bending moment diagrams. Let's take a look at an example. This beam has an applied distributed force and a concentrated force. Let's quickly draw the shear force and bending moment diagrams. By using the free body diagram method, we can show that the bending moment curve for the section of the beam under the distributed force is defined by the quadratic equation negative 4x squared plus 34x plus 68. If we differentiate this equation, we get negative 8x plus 34, which based on the dm over dx equation above, we now know is the equation for the shear force curve in this section of the beam. If we differentiate again, we get negative 8, which is the equation for the distributed force. This is a great way to sense check your shear force and bending moment diagrams. Another way of checking your diagrams is using the area equations I mentioned earlier. The area under the shear force curve, highlighted here, is equal to 34 times 2, which is 68. This is equal to the change in bending moment over this section of the beam. We can also calculate the area under the shear force diagram for the beam section under the distributed force. The total area of this section is equal to 72.3 minus 12.3, which is 60. This is equal to the change in bending moment of 60 kilonewton meters over this section of the beam. Where concentrated forces are applied, there is a sudden jump in the shear force diagram, and where concentrated moments are applied, there is a sudden jump in the bending moment diagram. These equations will not be applicable across discontinuities in the diagrams. One final observation we can make based on these equations is that when the shear force is equal to 0, the bending moment curve will be at a local minimum or maximum. Let's look at one last example. Here we have a cantilever with an applied concentrated moment of 120 kilonewton meters and a distributed force of 6 kilonewtons per meter. Again, we start by drawing the free body diagram. Because the support is fully fixed, we have vertical and horizontal reaction forces, Ra and Ha, and a reaction moment, Ma. Let's look at our first equilibrium equation. The sum of forces in the vertical direction is equal to 0. In this case, the only forces acting in the vertical direction are the reaction force Ra and the distributed force. So Ra is equal to 6 times 3, which is 18. Ha is the only force in the horizontal direction, so it must be equal to 0. Next, we can take the sum of the moments acting at point A. In calculating the moment caused by a uniformly distributed force, you can remember that it is equal to a concentrated force located in the middle point of the load. This gives us Ma equals 21. To calculate our shear forces and bending moments, we will start on the left side of the beam and move towards the right. This is our first free body diagram. The shear force calculation is easy, as we only need to consider the reaction force of 18 kilonewtons. The bending moment needs to take into account the reaction moment and the reaction force. At x equals 0, the bending moment is equal to the reaction moment of 21 kilonewton meters. As we move to the right, we also need to consider the moment caused by the 18 kilonewton reaction force. This gives us the equation for a straight line. We can then move our cut to the right of the concentrated moment. The moment won't affect the shear force, which will remain constant at 18 kilonewton until we reach the distributed force. But it does cause the bending moment to suddenly drop by 120 kilonewton meters. After the drop, the bending moment is again defined by a straight line. Things get a little more tricky when we reach the distributed force. We can replace the uniformly distributed force by an equivalent concentrated force with a magnitude of 6 multiplied by the length x over which the force is applied. This force is located at a distance of x over 2 from our cut. We can then calculate the shear force and bending moment equations using the normal approach. The bending moment in this section of the beam is defined by a quadratic equation. No loads are acting on the small 1 meter section to the right of the distributed force, so shear forces and bending moments in that section will be equal to 0. Although we can't calculate displacements from these diagrams, we can use the bending moment information to predict the deformed shape of the beam. Where the bending moment is positive, the beam will be sagging, and where it is negative, it will be hogging. Where the bending moment is 0, the beam will be straight. That will give us a deformed shape that looks something like this. That's it for this quick look at shear forces and bending moments in beams. I hope you learned something new. In this tutorial, I am going to teach you how to In this tutorial, I am going to teach you how to draw the shear force and bending moment diagram of a simply supported beam carrying a uniformly distributed load over its entire span. Before watching this tutorial, if you haven't subscribed to my channel, please subscribe it and don't forget to press the bell icon to remain updated. Consider a simply supported beam carrying a uniformly distributed load W per unit length over its entire span. The support reactions will be equal and their magnitude will be equal to half the total load acting on entire span. So due to the UDL, the support reaction at A will be equal to support reaction at B equal to total load divided by 2, while total load is the load intensity W into this span L divided by 2, which will be equal to WL divided by 2. Now consider a section XX at a distance of x from left end A. The shear force at this section will be equal to summation of all the forces acting on left portion of this section XX. So shear force at this section will be given by Fx equal to plus Ra minus W into this distance x equal to plus WL divided by 2 minus Wx, which clearly varies by a straight line law. At point A, the value of x will be equal to 0. So on substituting this value in shear force equation, we will get the value of shear force at point A equal to plus WL divided by 2. At point C, x will be equal to L divided by 2. On substituting this value in shear force equation, we will get the value of shear force at point C equal to 0. And at point B, x is equal to L. On substituting this value in equation of shear force, we will get the value of shear force at point B equal to minus WL divided by 2. In order to draw the shear force diagram, we will start from the baseline AB. At point A, the value of shear force is plus WL divided by 2. So we will draw this plus WL divided by 2 to some scale above the baseline. And at point B, the shear force is minus WL divided by 2. So we will draw minus WL divided by 2 below the baseline at point B. And by joining these 2 points, we will get the resulting shear force diagram. The bending moment at the section XX will be given by Mx equal to plus Ra into x minus W into this distance x into x divided by 2, while this x divided by 2 is the centroid of this portion x, which will be equal to WL divided by 2 into x minus Wx square divided by 2. At point A, the value of x will be equal to 0. On substituting this value in bending moment equation, we will get the value of bending moment at point A equal to 0. At point C, x is equal to L divided by 2. And on substituting this value in bending moment equation, we will get the value of bending moment at point C equal to plus WL square divided by 8. And at point B, x is equal to L. And by substituting this value in bending moment equation, we will get the value of bending moment at point B equal to 0. In order to draw the bending moment diagram, we will start from the baseline AB. And since the maximum bending moment is at point C and equal to plus WL square divided by 8, so we will draw plus WL square divided by 8 to some scale at point C.
and at points A and B the value of bending moment is equal to 0. Since the bending moment equation for span AB clearly indicates that the bending moment from A to B varies by a parabolic curve. So we will join points A and B by a parabolic curve. This will be our resulting bending moment diagram. So this was all for today. We'll catch you up soon.
So for the materials, I hope this is clear for everyone of you. Why everyone of you are giving attendances now? I don't understand. It started at around just when I started the class. Amarjit Sonwar started giving the attendance, and now everyone is giving the attendance. I don't know why. Can anyone please tell me, those who have given the attendances, tell me the reason? Or should I mark all of them absent? Everyone is giving attendances. I am not asking any one of you to give attendances, right? So I'll mark all these people absent. Can if anyone from them does not give me any justification, can anyone give me any justification? Why are you giving attendances? Please, can anyone give me justification why you are giving attendances? All of you, in fact, all of you are giving attendances in the chat box when I have not asked for it.
Sir, can you share the link of that video, the two video?
I'll send you. But then,
Okay, sir.
but why your friends are giving attendances? I want that only.
Oh no, sir, I didn't give.
I know you have not given it, but this does not look good, right? This does not look good. Why your friends are giving? Can anyone please give me a justification? I'll mark all of them absent today. Network problem. It may disconnect. Okay, one people give network problem. Well, every one of you is having network problem today. So many people are having network problem. I don't believe that. Huh? So many people are having network problem or what today? Yeah. What about others? This is not good, right? This is not good. This should not happen actually. Other than that, you can ask me any doubt if you have. What happened? if you don't have any doubt.